Hello everyone. Welcome to a new lecture in the series of Control of Mechanical Systems. In this lecture, we will be discussing the mathematical modeling of mobile robots. Here is the overview of this lecture. We will be starting with a brief introduction to mobile robot. Then we move on to the modeling of mobile robot, where we derive the kinematic and dynamic equations for the mobile robot. In general, a mobile robot is a machine which can move around its environment. Mobile robots can be different types, such as wheeled robot, where the movement is achieved using wheels, and legged robot that can walk in a surface, and aerial robots such as drones which can move in a three-dimensional space. In this lecture, we are only focusing on wheeled robot, and specifically we will focus on differential wheeled robot, which is a mobile robot based on two separately driven wheels placed on its both sides. Figure 1 shows a schematic representation of differential wheeled robot, where we have wheels on both sides. We can call like left wheel and right wheel. Both of these wheels are associated with the electric motor, and we can control the torque given to each of these motors separately for adjusting their velocities. Let's say VL denotes the velocity of the left wheel and VR denotes the velocity of the right wheel. Then by controlling these velocities independently, we can adjust the velocity of the mobile robot. For example, if VL and VR are same, then the mobile robot will be having a linear motion where it moves in a straight line. And if let's say VR is lesser than VL, then the robot will be more moving towards the right hand side and vice versa. Here, let's say P denotes the current position of the mobile robot, which contains its position in the x and y coordinate and also its angular position denoted by theta. And let's say R denotes the reference position of the mobile robot, which contains the position in x and y denoted by xr and yr, and also its angular position denoted by theta r. Here, this V denotes the current velocity of the mobile robot, which can have an x and y component denoted by Vx and Vy. And similarly, VR denotes the reference velocity of the mobile robot, which can also have an x and y component denoted by Vrx and Vry. We can have these following terminologies associated with the mobile robot, where M denotes the mass of the mobile robot, B is the friction coefficient, J is the moment of inertia, D is the damping coefficient, VL and VR are the velocity of the left and right wheels, V is the linear velocity of the mobile robot, and omega is the angular velocity, and VR is the reference linear velocity. Then, as we seen in the previous slide, we can have P as the actual position, which contains x, y, and theta, and R as the reference position, which contains xr, yr, and theta r, that indicates the reference coordinates. Then, in the case of position tracking, our objective is to drive the mobile robot to its reference path. In other words, we need to make P is equal to R. So this reference path or this reference trajectory will be obtained using solving some path planning problem. Then we will be using some controller algorithm to make the mobile robot to follow this reference path. Or in other words, we need to make this P equal to R at all time instant. Now here, in order to design the controller, we need a mathematical model of the mobile robot, and its derivation will be discussed next. First, we will be deriving the kinematic equation of the mobile robot. Then we move on to the dynamic modeling. The kinematic model of the mobile robot can be represented as in equation number 1, where we have Vx is equal to V cos theta, which can be seen from this figure, where Vx is the x component of the velocity and theta is this angle. So we can see that Vx will be equal to V cos theta and Vy will be equal to V sin theta, and theta dot will be omega, where theta dot is the derivative of the angular position, which will be equal to angular velocity. Similarly, for the reference trajectory, we will be having Vrx will be equal to Vr cos theta and Vry will be equal to Vr sin theta, and theta dot will be equal to omega r. Now, for this mobile robot, we have the equation for the linear position, which is equal to r times angular position. Therefore, the linear velocity of the mobile robot can be obtained by Vl equal to r1 omega and Vr will be equal to r2 omega. Then by subtracting these two equations, we can have VR minus VL will be equal to R2 minus R1 into omega. And solving this for omega gives omega equal to VR minus VL divided by R2 minus R1. And this R2 minus R1 we can call as the wheelbase B. Therefore, we will be having omega is equal to VR minus VL divided by wheelbase. Similarly, we can have the linear velocity of the mobile robot V is equal to R omega, where R is the distance of the center of gravity of the mobile robot from the origin, and which we can also obtain as R1 plus R2 by 2. And here we have R1 omega will be equal to VR and R2 omega will be equal to VL. Therefore, we obtain the linear velocity of the mobile robot as VR plus VL by 2. Now, in differential wheeled mobile robot, the motion is controlled by adjusting the left and right wheel velocity separately. And here we have obtained omega is equal to VR minus VL by B and V is equal to VR plus VL by 2. Therefore, here if we see if VR is equal to VL, we will be having omega is equal to 0 and V is equal to VR equal to VL, which is characterized by only linear motion, where the mobile robot will be moved in a straight line path. And similarly, if VR is equal to minus VL, we will be having V is equal to 0 and omega is equal to 2 VR by V. And this is characterized by only rotational motion, where the linear velocity is 0 and the mobile robot has only angular velocities. And in all other cases, we will be having the motion will be as a combination of linear and rotational motions. Therefore, if we need to drive the mobile robot in a linear path, we just need to make VR is equal to VL. And if we want to move the mobile robot from this linear path and follows it in a curved trajectory, we just need to adjust VR and VL accordingly. Now, for the position tracking, our objective is to make X equal to XR, Y is equal to YR, and theta is equal to theta R. Or in other words, we need to make this error XR minus X equal to 0, YR minus Y is equal to 0, and theta R minus theta equal to 0. And here we are considering the error along the mobile robot direction, where PS denotes the direction along the mobile robot motion, RS denotes the direction orthogonal to the mobile robot motion. And therefore, we denote XE equal to PS and YE equal to RS, where PS is this distance and RS is this distance. And here we can see that if PS and RS are 0, then this P will become equal to R. Or in other words, the mobile robot reaches the reference position. Therefore, our objective is to make PS and RS equal to 0. In other words, XE and YE equal to 0. And using trigonometric relations, we can have PS will be equal to this distance plus this distance. And here we can see that this distance will be equal to PQ cos theta, where PQ is this distance. And here we can have PQ will be equal to XR minus X, and using which we have this distance will be equal to XR minus X cos theta. And then this remaining distance will be same as this distance if we complete a triangle here. And this distance we can see as YR minus Y sin theta. Therefore, we have PS is obtained as XR minus X cos theta plus YR minus Y sin theta. Similarly, we can obtain YE as minus XR minus X sin theta plus YR minus Y cos theta, and theta E will be equal to theta R minus theta. Then we can take the derivative of each of these variable for obtaining the error dynamics, where we obtain XC dot as in equation 8. And here we can substitute X dot, XR dot, and theta dot from the kinematic equation, which results in equation 9. And replacing this expression in green color with YE, we obtain XC dot is equal to VR cos theta E minus V plus omega YE, which gives us the error dynamics along XC. Similarly, we can obtain the error dynamics along YE as in equation 10 and the theta E as in equation 11. Then choosing the state variables as x1 equal to XE, x2 equal to YE, and x3 equal to theta E, and the control variables u1 equal to V and u2 equal to omega. gives us the kinematic model of the mobile robot for the error variables as in equation 12. Then in the case of position tracking, we just needed to stabilize this model to make x1 equal to 0, x2 equal to 0, and x3 equal to 0, which basically makes xc, ye, and theta e 0. Next, we move on to the dynamic model of the mobile robot, where we apply the force and torque balance equation along the mobile robot, which gives mv dot plus bv equal to f, where f is the applied force, m is the mass of the mobile robot, and b is the friction coefficient. And similarly, by applying the torque balance, we obtain j omega dot plus d omega equal to t, where t is the applied torque, j is the moment of inertia, d is the damping coefficient. Here, these two equations are obtained by applying the force balance and torque balance equations from the Newton laws of motion. Then, by defining the control input u1 equal to v, u2 equal to omega, v1 is equal to f, and v2 equal to t, gives us the dynamic model of the mobile robot as in equation number 14. In the controller design of mobile robot, we will be using both this dynamic model and the kinematic model. And our objective is to design these control inputs that will stabilize the kinematic model. In the next lecture, we will discuss the controller design for mobile robot, where we will be using the sliding mode control approach. That leads us to the end of this lecture. Thanks for watching.